Thank you for joining me in this video. I'm going to talk about graphically the limit as x goes to 0 of tangent x over x. So I'm going to do a sequence of graphs. So please be aware of that, not just one graph. You got to really love graphing to watch this video. Okay. Now, first we always try direct substitution. So it's going to be like this. Tan of 0 over 0. And then let's say you do this and you're like, I don't know how to interpret this. So, okay, get yourself a graphing thing. Any kind of software, calculator, whatever, put that in there. 10x, okay. And you're like, what? This is a crazy mess. How do I relate it to this seemingly simple looking thing? So because the x is going to 0, you're looking for tangent of 0. So you just got to zoom in on tangent of 0, which is this spot right here. And as you can see, the value of tangent of 0 where I'm pointing is 0. The y coordinate there is 0. So that means you just end up with 0 over 0. This is not defined. So it doesn't really answer our question, what is the limit, okay? So first instance of using a graphing feature. Next, what I'm going to do is I'm going to do it now the way you expect to do it with some steps algebraically on expression, but support each step with a graph. So limit as x goes to 0 of 10x times 1 over x. Is this allowed, this kind of step where we just rewrite things? How do we know that it's a valid step? Okay, so if you want to pin this down to something visual, so it doesn't feel so abstract and random, begin with the original. 10x divided by x, right here on the right side, please. I'm going to graph that, okay. You got to zoom in on where it matters the most. So that's the origin in this case. So I'm going to zoom in on the origin a little bit more right here. And you see this is what it looks like, okay. Now alone, from looking at this, you can tell the value of the limit is 1. So that's another way to think about it, okay. When x approaches 0 from the right side, the y coordinates go to 1. When you approach 0 from the left side, the y coordinates go to 1 right here. Look at the arrows and where they're positioned. Pause the video and really look at it very carefully. Okay, so that's something to do. But then you're supposed to show steps on the left side. So limit x goes to 0. I'm going to put sine x over cosine x times 1 over x. So is this valid? So go back to here. I'm going to start overlaying graphs. First, I'm going to overlay 10x times 1 over x to make sure that it matches the original. You see how they overlap perfectly? That means the original limit as x goes to 0 of 10x over x is exactly the same as 10x times 1 over x. Or the graphs would be different. Is that the same as sine over cosine times 1 over x? We check that part next. Okay, so overlay in the graph. Sine x divided by cosine x. We do it again, cosine x times 1 over x. Is this the same? It is, you see? It's the same graph every single time. They overlap perfectly. That means these are all valid steps on the left side here. And then I'm going to put the limit as x goes to 0 of sine of x, and then times 1 over cosine x. And now you might be like, let me fix this 1 second. 1 over cosine. You might be like, well, this looks really different now, at least to the eye. But is it? Well, you know what to do. You graph it. So sine x over x times 1 over cosine x. Graph it, and what do you see? It overlaps again. That means each of these steps here is valid. This is okay, this is okay, and this is okay. They all produce the same identical graph, so the algebra here is not changing anything. So what I mean by that is, imagine you take a step and you write something like limit as x goes to 0, and then you just write 10x, let's say this is the original, but then you put limit as x goes to 0, and then you just write it this way. Okay, so then you graph it. So let me do that. Let's say I'll make that one green, which is right now 10x times 1 over x, which is valid. I'm going to put times x, not 1 over x, right here, times x. Look at it carefully, please, very carefully. And you see, you get a completely different graph for the green graph. It doesn't match the original anymore at all. So this is what? This is bad, at least for the purposes of what we are doing. You can't just rewrite it this way. But at least the graph reveals it, even if your mathematical sense does it. This is just a bunch of symbols. To go from symbols to really seeing what the symbols tell you in graphs, that can be a very seemingly time-consuming journey, but at the same time, it gives you a lot more confidence for whether or not what you're doing is right or wrong and so on, okay? So just graph everything all the time, and you'll understand things better, okay? And build your confidence thereby. So I'm going to put 1 over x back here to make sure they overlap. And then I'm going to limit as x goes to 0 of sine x, okay, times the limit as x goes to 0 of 1 over cosine x. Now at this point, you really should ask yourself, could I graph this separately in one panel? This part here, right? Could I graph this in a separate panel, and can I just multiply the answers? This is a valid rule of limits, the product rule of limits. You should have learned it hopefully by now. Now this limit here, the first one on the left, is known to be 1. That's a famous limit. This one you can do by direct substitution. So you can just do 1 over cosine of 0. So that's 1 over 1, which is 1, like that. So you just end up with 1 times 1, which is equal to 1, which is the value of the limit, which remember was also supported back where I showed that it was equal to 1 just by looking at the graphs here, okay? But I also did a sequence of graphs to confirm that at each stage the algebra matched the original expression in terms of the graphs that are produced. So in other words, look at this carefully, please. Imagine you do something like this. I'm just going to take x squared, the famous example, because this applies in many different cases. Famous example. Imagine I have x plus 1 quantity squared, and then some people will write x squared plus 1 squared, and they're happy, right? They just write it this way, okay? So look at it very carefully now. Do the graphs support this claim, right? Is this valid? Do the graphs support it? Okay, so you just punch in x plus 1 squared. This is the original. That looks like this. And then type in the supposedly valid step. So that's going to be x squared plus 1. And now look at them very carefully, and what do you see? They don't overlap. So that means x plus 1 squared is not x squared plus 1 for sure. It's not valid to do that because the graphs, as you can see, do not match. So these are little lessons that you can discover through graphs. Just graph everything all the time. Lastly, I think that can happen, especially as we grow older, is there can be a lack of desire for learning new things. Sometimes you try to generate a desire from within, but the problem is there's nothing there, it seems like. So what we can try to do is just ask the universe, demand from the universe, right? More desire, in fact, infinite desire to learn and grow and expand your mind. Why not? Why? It's a perfectly valid demand. We are part of the universe. The universe has made us. We're not separate from it. By asking the universe for this, we have that right because we are a part of it. You know, honestly, I think what is a human being sometimes, and I think, you know what a human being is? It's literally the uncreated infinite power behind everything, hiding itself from itself with a seemingly limited intellect and awareness that we have. But it's so good, right, that we feel separate from the universe sometimes. Anyway, these are my little philosophical musings. Thanks so much for watching. Have an amazing rest of your time watching videos on YouTube.